We think we understand how things work cause and effect. You push something, it moves. You plant a seed, it grows. For centuries, this was the dream of science, the dream of a clockwork universe. The idea was simple. If you could just know the position and speed of every particle, you could predict the future perfectly. You could know everything that was ever going to happen. But that dream was wrong. The universe isn't a perfect clock. It's something far more interesting. It's messy. It's unpredictable, and it's governed by a principle we call chaos. Chaos theory isn't about total randomness or disorder. It's the opposite, in a way. It's about systems that follow strict, deterministic rules, yet their long-term behavior is impossible to predict. It's the hidden order within the apparent mess of the world. It's the reason you can't predict the weather next month, why a stock market crashes, and why a tiny event can change the course of history. It all started with a man named Edward Lorenz. He wasn't trying to change our view of the universe. He was just trying to predict the weather. In the 1960s, he built a simple computer model of the Earth's atmosphere. It was a set of 12 equations that described how things like temperature and wind speed changed over time. One day he wanted to rerun a simulation. To save time, he didn't start from the very beginning. He typed in the numbers from the middle of a previous run. But he was a little lazy. The computer stored the numbers to 6 decimal places, like 0.506127. Lorenz just typed in 30.506. He figured a tiny difference like that, 1 part in 1,000, wouldn't matter. It was like measuring a coastline and being off by a single grain of sand. It should have produced almost the exact same weather pattern. It didn't. At first, the new simulation mirrored the old one, but then, slowly, the two paths began to drift apart. After a few simulated months, the weather patterns were completely different. There was no resemblance at all. Lorenz was stunned. The tiny, insignificant rounding error had produced a catastrophic change in the outcome. The system was deterministic. The same input always produced the same output, but a slightly different input produced a wildly different output. This was the birth of chaos theory, and it gave us its most famous concept, the butterfly effect. Lorenz later joked that the flap of a butterfly's wings in Brazil could set off a tornado in Texas. It sounds like a metaphor, but it's a literal description of how these systems work. The official term is sensitive dependence on initial conditions. It means that in chaotic systems, tiny, immeasurable differences in the starting point can lead to enormous, unpredictable differences later on. This is why long-term weather forecasting is basically impossible. We can't measure the exact temperature and wind speed of every single molecule in the atmosphere. We can't track every butterfly's wings. Even if we could, the slightest error in our measurement would eventually make our forecast completely wrong. The system amplifies tiny errors until they dominate the whole thing. You see this principle everywhere once you start looking for it. Think of a game of pool. You can predict the first shot pretty well, but can you predict where all the balls will be after 10 bounces? No. The tiniest difference in the angle of the cue stick, a microscopic dent on a ball, or a bit of dust on the felt gets magnified with every single collision. After a few bounces, the system is completely unpredictable. It's not random. It follows the laws of physics perfectly. But it's chaotic. This idea shatters the old clockwork dream. It puts a fundamental limit on what we can know. The problem isn't our measuring tools. The problem is the nature of the system itself. Even with perfect models and near-perfect data, we are blind to the long-term future of chaotic systems. But chaos is not just about unpredictability, it's also about structure. As Lorenz watched his computer model run, he noticed something else. The weather system it was simulating never repeated itself exactly. But it also didn't go off into infinity. It didn't produce impossible results like negative wind speeds or infinitely high temperatures. The system always stayed within certain boundaries. When he graphed the output, a beautiful and mysterious shape began to emerge. It looked like a pair of butterfly wings, or a twisted figure 8. The system would loop around one wing for a while, then suddenly jump to the other, loop around there, and then jump back. It was always moving, always changing, never landing on the same point twice, but it was always confined to this specific shape. He had discovered what we now call a strange attractor. An attractor is simply what a system settles into. Think of a pendulum. If you let it swing, friction and air resistance will eventually slow it down. It will settle into its attractor, which is a single point hanging straight down, motionless. That's a simple point attractor. A planet orbiting the sun has a simple orbit attractor. It's a predictable, repeating loop. A strange attractor is different. It's a map of a chaotic system's behavior. It's the path the system follows. It's a region of possibilities where the system is drawn, but within that region, its movement is forever unpredictable. It has order and structure, but it's an infinitely complex structure. The system is always on the attractor, but never in the same place twice. This is the beautiful paradox of chaos. It is simultaneously free and constrained. The weather is unpredictable day to day, but we know it will stay within the bounds of what we call climate. The temperature in Chicago in July will fluctuate, but it won't be 50 degrees. It's tethered to its strange attractor. Stirring cream into your coffee is another good example. The swirls are complex and never repeat. You can't predict the exact pattern, but the cream doesn't suddenly jump out of the cup. It stays within the boundaries of the liquid. The swirling patterns are a temporary, visible, strange attractor. It's a dance of order and unpredictability. This leads to the third major idea of chaos theory, fractals. When mathematicians looked closely at the structure of these strange attractors, they found something amazing. They had a property called self-similarity. If you zoomed in on a tiny piece of the attractor, it looked like a smaller version of the whole thing. There, zoom in again, and you'd see the same pattern, and again, to infinity. This is the defining feature of a fractal. It's a shape whose complexity is the same at any scale. But nature is full of them. Think of a fern. The whole frond has a certain shape, but each little branch off the main stem is a miniature version of the frond. And each little leaflet on that branch is an even smaller version. Or think of a coastline. From a satellite, it's a jagged line. Zoom in to a map of a single bay, and it's also a jagged line. So zoom in further to a single stretch of beach, and the line between water and sand is still jagged and complex. A classic question was, how long is the coast of Britain? The answer, discovered by the father of fractals, Benoit Mandelbrot, is that it depends on your ruler. The smaller the ruler you use, the more nooks and crannies you can measure, and the longer the coastline becomes. In a sense, its length is infinite. Coastlines, lightning bolts, snowflakes, river deltas, the branches of trees, the network of blood vessels in your lungs. These are not the simple spheres and cones of classical geometry. They are the shapes of the real messy world. They are the geometry of chaos. Fractals are created by repeating a simple process over and over again. A tree grows by repeating a simple rule branch. A snowflake forms by repeating a simple rule of how water molecules crystallize. This is a profound insight. Immense complexity can arise from very simple rules. You don't need a complicated blueprint to create a complicated object. You just need a simple process and a lot of repetition. So how does all this, the butterfly effect, strange attractors, fractals actually govern our world? It's not some abstract mathematical curiosity. It's at the core of how reality functions, from the microscopic to the cosmic. Let's start with biology. Your own heartbeat is a good example. You might think a healthy heart is one that beats like a metronome, perfectly regular. But it's not. A healthy heartbeat has a slight chaotic variability. The time between beats is always changing a little. This variability allows the heart to adapt quickly to changing demands, like standing up suddenly or running for a bus. Doctors have found that a heart that becomes too regular, too periodic, is often a sign of disease. The chaos is a sign of health. On the other hand, extreme chaos in the heart is fibrillation a deadly, disorganized state. Life exists in that sweet spot, on the edge of chaos, between rigid order and total disorder. Population dynamics are also chaotic. The number of fish in a lake or insects in a field doesn't follow a simple, predictable curve. It follows a boom and bust cycle that is highly sensitive to initial conditions. A slight change in the number of predators one year, or a small shift in the weather, can lead to a population explosion or a complete crash years later. The underlying equations are simple, but the behavior they produce is impossibly complex. Even the way our brains work seems to be chaotic. The firing of neurons is not a simple linear process. It's a vast, interconnected network where small signals can be amplified into large-scale thoughts or actions. Some researchers believe that the brain operates at the edge of chaos. This state allows it to be stable enough to store memories, but flexible enough to form new connections, to learn, and to be creative. An epileptic seizure might be what happens when the system's chaos collapses into a kind of pathological order, with millions of neurons firing in a rigid, synchronized, and destructive way. Chaos theory also rules economics and finance. The stock market is perhaps the most famous chaotic system we've built. Countless agency investors, algorithms, banks, pension funds are all interacting, each making decisions based on limited information and reacting to the decisions of others. It's a massive feedback loop. A piece of news, or even a rumor, can be like Lorenz's butterfly. It can ripple through the system, getting amplified at each step and lead to a huge market rally or a devastating crash. This is why no one can consistently predict the market. The system is too sensitive. The number of variables is too vast. It's not random. People are making what they believe are rational choices, but the collective result is unpredictable. Then there is history and society. We like to think of history as a neat story, a series of big events caused by big people. But chaos theory suggests a different view. History is a chain of butterfly effects. Think of the assassination of Archduke Franz Ferdinand in 1914. It was a single, relatively small event. But in the hypersensitive political climate of Europe at the time, that one bullet flap cascaded into World War I, a conflict that killed millions and reshaped the entire globe. Was the war inevitable, or was it the result of a chaotic system tipping over a critical point? Social trends, fashions, and the spread of ideas work this way too. A single video can go viral and change a cultural conversation overnight. A handful of people starting a protest can trigger a nationwide movement. These systems are highly interconnected and prone to feedback loops. It's impossible to know which spark will fizzle out and which will start a fire. Even something as mundane as a traffic jam is a product of chaos. On a highway with cars flowing smoothly, one person tapping their brakes unnecessarily can create a ripple effect. The car behind them brakes a little harder, the one behind that harder still, until miles back, traffic comes to a complete standstill. This phantom traffic jam, with no accident or obstruction causing it, is a classic example of how complex, unpredictable behavior emerges from the simple rules that individual drivers follow. This has a profound effect on how we should see the world and our place in it. The old Newtonian dream of perfect prediction gave us a sense of power, a sense of eventual mastery over nature. This chaos theory teaches us humility. It tells us that there are fundamental limits to our knowledge. There are things we simply cannot predict, not because we are not smart enough, but because the universe is built that way. This might sound depressing, but it can also be liberating. If the universe were a predictable clock, then free will would be an illusion. Everything would be predetermined. Chaos, with its inherent unpredictability, leaves room for novelty. It means the future is not set in stone. The world is constantly being created. Tiny actions can indeed have huge consequences. This gives a certain weight and responsibility to our choices. You don't know which of your actions will be the butterfly that changes everything. It also changes how we should try to solve problems. If you're dealing with a simple linear system, you can look for a single cause and a single solution. But if you're dealing with a complex, chaotic system like an economy, an ecosystem, or a social organization, that approach will fail. Pulling one lever can have unforeseen consequences all over the system. Instead of trying to predict and control, the goal becomes to understand the system's dynamics. We need to look for the strange attractors, the underlying patterns. We need to build systems that are resilient and adaptive, that can handle surprise. We need to nudge and guide rather than command and control. For example, instead of trying to perfectly predict and prevent every financial crisis, a chaos-aware approach would be to build a financial system with fire breaks, regulations that prevent small failures from cascading into a total system collapse. In conservation, instead of trying to maintain an ecosystem in a single, static, perfect state, we recognize that it's a dynamic system that needs to fluctuate. The goal is to preserve its resilience, its ability to bounce back from shocks like fires or disease. At a personal level, chaos theory can be a comforting framework for life itself. Our lives are not neat, linear paths. They are messy, unpredictable, and sensitive to small events. A chance meeting, a stray comment, a book you happen to pick up, these can change the entire trajectory of your life. You can't plan for everything. You can't control the outcome. Your life is not a simple problem to be solved. It's a chaotic system to be lived. It has its own strange attractor. You have your habits, your personality, your values that keep you bounded, that make you ooh. But within those bounds, your path is unpredictable and full of infinite possibilities. Chaos theory brought about a true revolution as profound as relativity or quantum mechanics. It was a moment when science looked at the messiness of the real world, so a cloud, a waterfall, a crowd of people, and decided not to ignore it as mere noise. It decided to look right into the heart of the mess and find the beautiful, intricate order hidden within. It showed us that the world is a place of endless creativity. From simple, repeating rules, nature builds infinite complexity. From the dance of chaos, structure emerges. We live in a universe that is not a static machine, but a living, evolving process. It is a world where the flap of a butterfly's wings truly can matter, and that makes things a lot more interesting. It's a world where nothing is certain, but everything is connected. And in that unpredictability, in that sensitivity, lies all the danger, all the beauty, and all the hope of being alive.